from the planet Earth first set foot upon the moon, July 1969, AD. It came in peace for all mankind.
In July 1969, man achieved his historic goal. He landed on the moon and returned safely. And as we continue through this second decade of spaceflight, missions in Earth orbit, to the moon, and perhaps someday to the planets are still commanded from this Mission Operations Control Room at the Manned Spacecraft Center, 22 miles southeast of Houston, Texas. Of course, before any such space mission is launched, a vast amount of work must be performed. Landing men on the moon, for example, was the result of years and years of exhaustive research, development, manufacturing, and testing by more than 300,000 people in private industry, universities, and government agencies throughout the United States. NASA's Manned Spacecraft Center was directly responsible for the spacecraft, the crew, the design, and control of that most historic moon landing mission. The center continues as the creative source of missions for the benefit of mankind. Located on 1,620 acres on the edge of Clear Lake, the site was selected and the center was built to meet the needs of America's space flight programs for the foreseeable future. Here there is a year-round climate for outdoor training and tests. One of the nation's 3 largest ports and waterborne transportation facilities, and progressive educational institutions. As initially planned, there are 34 main buildings at MSC, housing offices, laboratories, computer complexes, and testing facilities. A single unified center where spacecraft and mission profiles are designed, where spacecraft and systems are tested, and from where their manufacture by private industry is contracted and monitored. Here also, flight crews are selected and trained. And as we have seen, missions are commanded from liftoff to recovery. The United States has achieved preeminence in space technology and continues its leadership in the second decade of space flight. As in the past, NASA's Manned Spacecraft Center, MSC, with its teams of scientists, engineers, executives, and technicians, is responsible for tomorrow's manned spaceflight programs. Inside the buildings at MSC are to be found equipment and activities unlike those of any city in the world. Echo-free anechoic chambers, as noiseless as outer space. A test facility reproducing the shattering noise and vibration of a rocket launch. Cavernous, airless chambers for testing spacecraft and men in pockets of ultra-high vacuum resembling outer space. A huge centrifuge for flight acceleration training and testing. The facility is also used for simulating moonwalks as flight crew members are subjected to sensations at 1/6 of the Earth's gravity, which is the amount of gravity on the moon. At MSC, there are research offices and laboratories for analytical studies, design, development, test, and evaluation for spacecraft systems of guidance and control, propulsion, electronics, crew systems, including spacesuits and other life support systems, instrumentation, communications. At MSC is one of the largest computer complexes in the world, and the fantastic one-of-a-kind Mission Control Center, America's command post for manned space voyages. The building contains mission control rooms on the second and third floors. The duplicate rooms provide the capability for detailed preparations for missions, for the vast amount of training essential to mission success, for simulations and problem solving before, during, and after a mission, and for the direction and control of the actual missions. Responsible for detailed control of the mission is the flight director, who commands the mission. For an Apollo moon mission, about 20 specialists assist the director in the control room, and another 250 technicians and administrative personnel support mission control in adjacent rooms, such as this real-time computer complex. Here is some of the computing equipment that calculates flight paths and solves other problems of space missions. The solutions are transmitted to the spacecraft and automatically fed into the onboard computer and guidance system to keep them up to date. In this display area, computer-driven data displays instantly, on a real-time basis, reveal the spacecraft's location, velocity, and other conditions derived from tracking the spacecraft and communicating with the crew. In addition to the specialists in the mission control room and at the real-time computer complex, many experts stand by in other areas to provide support as needed. In the Apollo 13 crisis, the safe return of the men in their crippled spacecraft was due to the round-the-clock expertise and close liaison of these experts with the engineers and technicians of private contractors throughout the country. Flight Operations also coordinates the worldwide tracking network and recovery forces deployed by the Department of Defense in cooperation with nations around the world. As in every other aspect of our country's space program, tracking and recovery facilities have been carefully planned to meet the requirements of increasingly complex missions. Like the facilities, the citizens of the Manned Spacecraft Center are exceptional, both for the field of human endeavor they have chosen to work in and for the dedication they bring to their work. And a few dozen of them are specialists of a kind never before known in human affairs, the astronauts. To Houston, they have come from all over the country, from small towns and large. At the Manned Spacecraft Center, their education and skills are sharpened for the specialties of space flight, exploration, and space science. Supplementing general academic courses and training, astronauts are given frequent briefings at the other spaceflight centers. At MSC, they are given instruction and practice in the particular operations of specific missions. They practice landing the lunar module on the moon using unique lunar landing training vehicles. They use simulators to develop skills required to rendezvous and dock the lunar module with the command module in order to bring the lunar surface explorers back to Earth. Such specific operational training includes hours of simulated flights and mission trainers. Trainees solve various problems in all different phases of a particular space mission and become totally familiar with spacecraft instruments and controls. In the course of their training, the astronauts also help to develop and test various items of equipment. This brings us to another complex area of support for our manned spaceflight programs, the engineering and development laboratories and test facilities at MSC. A challenging area of engineering and development is that of crew systems. To qualify for selection as an astronaut, a person must possess certain physical and mental characteristics. But after his selection, unlike the spacecraft, he can't be physically redesigned. Instead, the engineers at MSC must design spacecraft, spacesuits, and all life support equipment for the human being so he can take with him a livable environment for survival in the newly encountered regions of outer space. Such mobile environments do not have to contain all the comforts of life on Earth, but they must at least accommodate minimum human needs. To determine minimum tolerances, space medicine specialists at MSC conduct a variety of experiments. In the airless, pressureless vacuum of space with extremes of heat and cold, a livable environment can be provided by a portable life support system and a pressurized suit for use outside the spacecraft, and by environmental control systems in the pressurized spacecraft cabin. The crew must also be provided with food and water and waste disposal systems. During space missions, medical data are telemetered to doctors on Earth who analyze the physical condition of the astronauts from their temperature, blood pressure, and heart rate. Spaceflight itself yields the best data about man's ability to function in outer space. But invaluable tests of both men and equipment are conducted in the Manned Spacecraft Center's Space Environment Simulation Laboratory. The facility contains 2 huge vacuum chambers along with auxiliary facilities. Chamber A is the larger of the two, 120 feet high and 65 feet in diameter. Complete spacecraft up to 75 tons can be tested in environments like those of outer space and the moon surface. Chamber B is 43 feet high with a diameter of 35 feet. Chamber B is used primarily for astronaut training, for development of spacesuits, and personal life support equipment. It is also used for environmental tests on the lunar module. In both chambers, solar simulators can beam intense rays during a test, equal to those of the sun, unfiltered by Earth's protective atmosphere. The vacuum, which can be created by pumping out the air in either chamber, is close to the hard vacuum of space. One of the most versatile of the large test facilities performs vibration and acoustics tests Kraft Center scientific and engineering work, valuable benefits have resulted for the non-space world most of us live in. Over 3,000 items and processes in our everyday life are spin-off benefits from the space program. By using newly developed flame-resistant compounds, for instance, we can reduce the risk of fires on a wide variety of items, from draperies to newspapers. Paper, wallboard, and other materials are treated in their manufacture. Data about the compounds and processes are being widely disseminated through meetings and symposiums at the Manned Spacecraft Center. And the new fireproofing has already benefited many industries and products. Perhaps the greatest benefits from the manned spacecraft program are in the realm of the intangible, man's knowledge of his universe. In our search for answers, the importance of MSC's Lunar Receiving Laboratory can't be overstated. From the very first Apollo lunar landing mission, moon rocks and soil samples were rushed to the LRL for many preliminary examinations and classifications. Specimens were then distributed to scientists throughout the world. In addition to biological analyses of moon samples, other properties of lunar rocks and soil have been investigated. For example, certain common plants of Earth were exposed to lunar material and revealed growth rates 3 to 4 times normal. Physical, chemical, and mineralogical properties have been studied, utilizing, for instance, the most advanced gas analysis equipment to detect and analyze minute traces of gases emitted by the specimen. Radioactivity is another significant property in identifying unknown substances. At the Lunar Receiving Laboratory, buried 5 stories below the ground, is the most effective low-level radiation counting facility ever built. From studies of lunar rocks and soil, we now believe that the moon is as old as the Earth and possibly dates to the beginning of the solar system. Knowledge of the moon has also been accumulated daily from transmissions to Earth by instruments installed on the moon by Apollo astronauts. Seismometers, for instance, have reported moonquakes occurring at precise monthly intervals. Other instruments have sent back data on such phenomena as magnetism and solar radiation. While spacecraft and outer space missions are being designed and developed, Earth resource sensors and remote sensing techniques are also being developed by the Manned Spacecraft Center aircraft programs. These range from studies of the water areas attracting tuna fish off the Oregon coast to earthquake analysis assistance to Peru. As shown in these infrared pictures, the earthquake triggered a landslide that buried an entire village except for a statue of Christ. Both low-level and high-altitude aircraft, such as this specially modified RB-57, are used in such studies. The Earth Resources Survey Program is one of the tools which can be utilized in expanding man's understanding of his surroundings on Earth. The program is developing the technology and photographic and sensing data useful in man's management of his environment. For example, in these aerial photographs, the orange streaks clearly show the drift of an oil slick after an offshore oil well explosion. As another example, one farm crop can be distinguished from another on the basis of the patterns made by the crop's radiance in several spectral bands. This could make possible a regional census of agriculture from aircraft and a national or even a worldwide census from spacecraft, with consequent impact on future growing, markets, and price stability. Also, healthy crops potentially can be differentiated from diseased. These sequential pictures show the development of corn blight over a period of weeks in 1971. Using infrared cameras and multispectral scanners from aircraft, such crop data may be compiled to aid in farm management and improve the health of our foods and fibers. Other uses of such techniques may improve our management of water resources, our oceans, lakes, and streams. The great improvements being developed in information gathering can be compared to the invention of the telephone or radio, a quantum jump in human communication. MSC aircraft during the past several years have logged thousands of hours flying missions for government and university scientists, gathering data on agriculture, forestry, geology, geography, hydrology, oceanography, and public health. Such work has been performed for other nations as well as our own. These aerial surveys of Jamaica, for instance, revealed hitherto undiscovered sources of fresh water. Here can be seen underground freshwater seepage into the ocean, detected by thermal infrared sensors. Another example of international cooperation is MSC's participation in the International Hydrological Decade, dedicated to advancing our knowledge of the extent and amount of rainfall, the depth and density of snowpacks, and the levels of rivers, lakes, and irrigation reservoirs. Earth resource knowledge and developments on a national and global scale were a major goal in building Skylab, the first new spaceship to follow Apollo. It is an Earth-orbiting laboratory for a crew of 3. For studies of a variety of Earth conditions, the Skylab Earth Resources Experiment Package was designed with 5 different kinds of sensors, including a multispectral camera and scanner, infrared sensors, and microwave receivers. Ultimately, it is believed substantial benefits to living conditions on Earth could come from mapping. From surveys of mineral, agricultural, and ocean resources. From urban development studies. And from measurements and remedies developed to reduce and control pollution of the Earth's air and water. Skylab was also designed to carry several telescopes to study the sun from 230 miles above the Earth's lower atmosphere, and to obtain medical data on the effect of long-duration spaceflight on men. From the experience of Skylab crews remaining up to 8 weeks in space, future spaceflight systems such as those providing artificial gravity can be designed if necessary. Medical measurements and studies made of the effects of zero-G on the human body include measurements on the heart and cardiovascular system performances, the determination of sleep states, measurement of mineral balances, studies of metabolic exposure, and the study of long-term effects on the crewmen. Other biological experiments reveal effects of zero-G on cells, small animals, and insects. This model represents one of several possible designs studied in another advanced program under MSC's leadership, a 2-stage reusable space shuttle. It has an unmanned recoverable booster stage and a manned orbital stage, which can return and land at a regular airport. Under the direction of MSC engineers, difficult design problems of aerodynamics, stability, and control are overcome by such means as these drop tests of 1/10 scale models of the shuttle at White Sands, New Mexico. One of the many uses of the reusable shuttle may be as a new kind of spacecraft, a mobile space van or laboratory, piloted by astronauts, but carrying specialists from every science into space to conduct their own experiments and investigations. And the reusable space shuttle will greatly reduce the cost of unmanned space flights. It will take the place of an entire family of expensive launch vehicles which can only be used once, but which have been needed to place in space weather, communications, and other Earth-orbiting satellites. With the shuttle for transport, technicians will be able to deliver automated satellites to Earth orbit and will be able to repair, maintain, and refurbish them, or to reposition or retrieve them for return to Earth. The reusable shuttle will revolutionize spaceflight and bring forth a new era of low-cost space transportation with potential uses and applications as inconceivable today as were those of aircraft in the early 1900s. By combining the reusable shuttle with a permanent orbiting space station, a greater integration of scientific missions will be possible. The final decades of our fast-flying 20th century will almost surely bring forth a marvelous array of advanced scientific and technological facilities to use in this, our new domain beyond the Earth. And so, the men and women of the Manned Spacecraft Center, together with their colleagues in other government centers and private industry, continue with the same ingenuity, persistence, and care already demonstrated in the Mercury, Gemini, and Apollo programs, working to apply the results of Earth resource programs and to convert the undeciphered facts of outer space into knowledge beneficial to mankind.